This is the first of a sequence of videos where we're going to be trying to increase your three-dimensional vocabulary. You've had a fair amount of practice in 2D looking at how equations become graphs and vice versa, right? And you know what sine curves look like, and you know what exponential curves look like, and quadratics and things like that. You have a vocabulary of curves in 2 dimensions. And so we want to increase that now to surfaces. How do equations in x, y, and z turn into graphs in x, y, z space? Now, the set of surfaces we're going to focus on here in this section is what are called quadric surfaces. And quadric surfaces are surfaces whose equations can be written in this form: ax squared plus by squared plus cz squared plus dxy plus exz plus fyz plus gx plus hy plus iz plus k equals 0. Okay. This is essentially the three-dimensional cousins of the conic sections that you may have done in a pre-calculus class. You may recall that conic sections we wrote this way: ax squared plus bxy plus cy squared plus dx plus e plus f equals 0. Right? It's essentially, the equation can be written in a form where all of the terms are either quadratic, linear, or constants. Right? With two variables, you had x squared or y squared and xy. Those are your quadratic terms. Then you had linears, dx, ey, and the constant f. Now with three variables, I've got a bunch of combinations of quadratic terms: x squared, y squared, z squared, and then the product of any two of them: xy, xz, yz. Those are all my quadratic terms. I then have three linear terms: gx, hy, and iz, and then of course the constant term, which is essentially each of those variables to the 0 power. So there are a bunch of different things that happen depending on what A, B, C, D, E, F, G, H, I, J are. What values of those constants do we have? Now, the first set we're going to look at are cylinders. Now, cylinders are actually a category unto themselves that overlaps with quadratic surfaces. Now, you may think you know what a cylinder is. You may be right. Right? When I initially think of a cylinder, I think of a long tube. I think of something that's got a circular cross section, and it's extruded in the perpendicular direction, infinitely long. So it's this really long circular thing. I like to say they're long and they're straight. Sorry, they're round and they're straight. Round in one direction, straight in another direction. Now, an example of such a thing would be this. What I'm looking at here is the xy plane. This is essentially x squared plus y squared equals 4. So the coefficient in front of the x squared is 1, the coefficient in front of the y squared is 1. The constant is, well, the way I had it written, -4, but I moved it to the other side of the equation. And all the others are 0, right? This is quadratic in x, is quadratic in y. However, it doesn't have any z's in it. So because it doesn't have any z's in it, then the graph can be, the z coordinate can be anything. So as long as the x and y satisfy the equation of that circle, x squared plus y squared equals 4, circle radius 2, then you just let z be anything you want, and you get this thing called a cylinder. So from the point of view of quadric surfaces, the way we're going to be able to initially recognize cylinders quickly is if one of the variables is missing from the equation. So this one, x squared plus y squared equals 4, is missing the z. This one right here is z equals x squared, so it's missing the y, which means in the y direction, it can be anything you want. In the xz plane, this looks like a parabola. But because there's no y in it, the graph of this in 3D is a cylinder, right? So it's When I think of a cylinder in general, I think of give me any curve, pick a curve, any planar curve, and then extrude that curve in a perpendicular direction. Okay. So for what we're doing, if one of the variables is missing from the equation, then you definitely can extrude in that direction whatever variable is missing. And you have a cylinder. This I would call a parabolic cylinder, whereas the standard cylinder I might call a circular cylinder. Or if it was an elliptical cross-section, I might call it an elliptical cylinder. Give me the name of the shape of the curve and then say cylinder. Circular cylinder, parabolic cylinder, whatever. So two things. One is eliminating one of the variables. So get rid of the y squareds, get rid of the y, so that one of the variables is there. Then it's going to be a cylinder. That's going to mean it's a cylinder parallel to one of the axes. It's possible to have cylinders tilted off in different directions. We're not going to get into that here. With a bit of linear algebra and change of coordinate systems, it's not too hard to do. And you'll find that what happens is you start getting these terms that have combinations of x and y or y and z to tilt things off into different directions. Now, non-standard cylinders, essentially we've already seen one. It's quadratic, that parabolic cylinder, right, that I used a quadratic in x and linear in z. But the notion of cylinder is even bigger than that. It's not just quadric surfaces can be cylinders. There's other things that can also be cylinders. So let's try another example. Here is y equals sine x. It's your standard sine curve. I'm only showing, from minus pi to pi. Actually, it looks like minus 3 to 3, actually. But to say y equals sine x, that equation has no z in it. So if I'm thinking of this as describing a surface in space, well, then z can be anything you want because it doesn't change the truth of the equation. And how do I flip this around? Here we go. Come on now. In the z direction, I can just slide that sine curve as far as I want. So this would be a cylinder in a sense, because it's curvy in one direction and it's straight in the other direction. Actually, thinking about that, planes, we've already looked at planes. Plane is straight curve, then extruded in a direction. Those would also be cylinders in a sense. I would call them planes, but they are cylinders from the definition of take a planar curve and then extrude it perpendicular to the plane that the curve is in. Let's see, there's other things we could do. Here's a polar curve. The equation of this polar curve is r equals 2 plus 3 sine theta. So you could convert that to x's and y's if you really wanted to. It's not pretty, but it's not difficult necessarily to convert it. But that's just in the xy plane. There's no z involved. Right? This is not a quadric surface because its equation cannot be written just in terms of quadratic, linear, and constant terms with respect to your variables. This has trig functions involved and whatnot. It's a little bit more complicated. But I would call this a cylinder because it's a planar curve. It's that limachon with an inner loop, and then it's extruded in a direction perpendicular to that plane. A cylinder. For what you're going to be doing in your homework, cylinders are most readily recognizable because we're just doing quadric surfaces for the most part. And if the equation is missing one of the variables, you got a cylinder.